Okay, so normally I would have you give me feedback in class about how much the video made sense and I'd go off your questions. So I'm really hoping that the order I go in is one that will work for you. Um, I liked this video because it gave you a visual to prove to you that you could add an infinite number of numbers together, but not get infinity as your answer. Now, sometimes you will get infinity. It depends on the rate that you're multiplying by. So, first of all, let's talk about that rate. Um, so here I've got graphed the same functions that we had here. Just this, I put numbers in. Big difference is I'm going to call this y value a g of x and this y value f of x just so I can keep them straight. And then I have sliders on my rate and my starting value so that I can move those around. Now, something that's very important that you see here on this function is that these two lines come together. In fact, they do something called converge. Not every series you add together will converge. It's only under very specific circumstances, which I'll get to in a little bit, where your series will converge with a finite number, with an actual number. Infinity is not actually a number, remember. Okay, so let's start there. It's really easy to determine this place where these lines, or to determine if your function will diverge or not, or converge, based on your rate. You can see here that the way I've got my equations set up, let's make sure I've got this on, perfect. This bottom line here is your y equals x, and this top line is your y equals rx plus a, which in this case, it's just the line y equals 1x, or just x, plus 1, because of what my rate and my starting value are set to. So hopefully it does make sense to you that this function starts when y is equal to 1. Now, will these lines ever converge? Hopefully you said no. The reason for that is they're parallel to each other. I know those are the markings we use for triangles, but I'm going to go ahead and use them here. These lines are parallel, and so they do not converge. If they do not converge, they diverge. Don't know if I spelled that right. I should have looked it up beforehand. All right, we'll just deal with it. Any series, when you add up all of your terms, let's say I equals 1, which means I really should use an I here instead of an N. Anytime you start adding up things that diverge, they will add up to equal infinity. I learned it as if you have, I don't know, like up at the mine, they have those conveyor belts where they drop rocks or sand onto a pile, that pile creates a cone. If your series is going to keep adding at least the same amount over and over again, or maybe even your amount doubles or triples as you go through specific intervals of time. If you drop that sand down and then this sand comes down and this sand comes down and it just keeps getting bigger and bigger and bigger, it should make sense that this pile is going to be infinitely large if you let it go for an infinite amount of time. And that's, of course, if you let it go for an infinite amount of time, which is what we're talking about when we talk about infinite geometric series. We do assume that it's going to go on forever. But what's really interesting to me is if you think about how big that pile of sand is, but the amount you'd keep dropping keeps getting smaller and smaller and smaller. I always hate it when I do that. Forgot to change my settings. By the way, this is a really handy tool if you have a what is it, Google Chrome, and you also have a writing surface, some sort of touch screen. I think it was called Markup is the app I added to be able to do these videos. Just a little plug for them. All right, so again, let's say you have your conveyor belt, but you're gonna drop a certain amount of stuff. But then your next amount you're gonna drop is only half of what you dropped before. And then the next bit is half of your half, or a fourth. And then the next bit you're going to drop, oh, that's way too big. Is going to be 1/8. If you start dropping smaller and smaller amounts into your pile of sand, then it turns out, as you drop these items off the conveyor belt, there is a very specific size that your pile will get, and it will not get any larger than that. This is going to be what happens when your lines over here converge. Now, the most important thing here is notice the difference. The first example I did, my first thing I dropped was one big, and then the next thing I dropped was 2 big. So it had that piece of 1 plus the piece that was 2 big. And then I dropped 3, so it had the piece that was 1 big plus the piece that was 2 big plus the piece that was 3 big. Whatever big means in this case. Whatever unit you want to use there. Here, though, I have fractions that keep getting smaller and smaller and smaller. So what that means here is your rate has to be something less than 1. Once you make it anything less than 1, you can see here that your lines are going to converge at a certain location. So let's take an example, pretty classic example, one that I see in the homework a lot is going to be, let's take the sum of 1/2 to the I power, where I goes from 1 to infinity. So in other words, I'm going to add 1/2 plus 1/2 squared plus 1/2 cubed plus 1/2 to the 4th plus ... So in other words, 1/2 plus 1/4 plus 1/8 plus 1/16 plus ... All right, so this means that my rate that I'm multiplying by, let's change colors on that. My rate that I look at as I go is I'm multiplying by 1/2. I multiply by 1/2. I multiply by 1/2. So that 1/2 is my rate. So if I take my slider and set it to the 1/2, okay, then I'm going to take this back to the home so we can see it, because I just moved my x values, that's why we couldn't see it. And then my a value, it does need to change too, because I need to think about what my starting value is. And my starting value is the first value here. My first value is 1/2, so I do need to change my a to a half as well. All right, so just right off the bat, what I see here is I predict that I will end up, oh, I was hoping that would stay. I would end up getting a sum equal to 1, because that's what the x value was here. Now in the equation, or in the video I had you watch, they tell you an equation here. Apologies for the line through the middle. They tell you an equation here that this equation is the equation that you're going to use for today's lesson. And so what I want to do is I want to explain to you why this equation works using this last example here. But if you have trouble understanding what I'm about to do, that is okay. I'm also going to show you just how to use the equation and go straight to your answer. Okay, so there are a couple different ways that I could show you how this is true. I'm going to go for the one that I think will make the most sense to you. And that is, I want you to see here, if I look at this whole idea of y equals x, I want to think first just about the x values that they are using on this graph. This first one here, by definition, because here on the y-axis, remember a in your y equals mx plus a is your starting value. They've been calling it that since your freshman year on purpose. This is going to be your starting value. And since your y, which is a, is equal to the x, this location here also has to be an a value, which is why here they make a point that this length of this slope triangle is going to be a. So I just want to explain what these pieces mean, and then I'll bring things together for you. So if I look at the next important value, they tell us that this length here is AR. Now that means that this is not the point AR. What it means is this distance from A is the length AR. Which means if you want to find the x value here, you would have to take this length plus this length, and you end up getting A plus AR, which I'm going to regret putting it over there that far, so I'm going to move where I wrote that ever so slightly to the left. So that's the point A plus AR. And then the next important x length they give us is about right here. And remember, that means that this length is AR squared. So this point here is this length plus this length plus this length, or A plus AR plus AR squared. And they keep doing this all the way up until they get to this final value, which if I add up all the pieces was A plus AR plus AR squared plus AR cubed plus AR to the fourth. It's starting to get kind of tiny in there, but plus dot dot dot, because it's going to go on to infinity. Oops, that's what I get for hitting play. Actually, let's play that out. So you can see that they're going to keep going as far as they can, and even they dot dot dotted after a while. Alright, and what I see here is this, by definition, is the sum of all your terms, going from your first term to your infinite term. So that's why this visual does work well in helping us to find our sum of our terms, when what we're doing is we're going to multiply by a common multiple over, oops, that's the wrong one, it's your rate, and over and over and over again. When you multiply by that common rate over and over and over again, that's our geometric sequence, and since we're going to do it forever, that makes it an infinite geometric sequence. Alright, so, and again, this only happens when your rate is going to be less than 1. And we're actually going to call the rate less than the absolute value if you want, because you actually can do it with negative rates as well, but only if those negative rates are fractions that are less than 1. You'll see some of those in your homework, and I'll get to those later. Don't worry too much about those right now. Okay, so I want to show you here as well that this whole summation idea that we have, adding together our terms, this actually does go for the y value as well. Like I said, this a is your starting value. It's got a height of a. At your next location, we established that we are going to use y equals x, which means you are going to use isosceles triangles, 45, 45, 90-degree triangles. In other words, your y height is equal to your x length, which is why we see over and over again that repetition. But to get to this AR, keep in mind that what you're doing is this is your x value that you're plugging into your equation. And again, this was the equation I'm using as my f of x equation. This is the one I'm using as my g of x equation. All right, so if I have sum rate times a plus a, don't you agree with me that we're going to end up getting an answer of a plus a times r, just if I rearrange the variables? That goes directly, because this is my f of x, this goes directly to what this y value is here, a plus ar. And then if I plug in the next x value to find what the height of my equation is right here, I'm going to take, let's erase all that, I'm going to get f of x is equal to r times my x value, which was a plus ar, and then plus a, so r times my x value plus my starting value. And if I distribute, I get, I'm going to put the a's first on purpose, ar plus ar squared plus a, which rearranged is a plus ar plus ar squared, for this height of this point right here. So what we see here is the x values that correspond to this line happen to match up to the term before whatever the y value comes to right here. And our goal is, if we add these far enough, if we add them an infinite number of times, we can see that we're getting the same terms on the left and on the right. And of course, even the easier way to think about this is we're looking for the place where these two lines come together. Now, when lines come together, you're looking for your point of intersection. Your point of intersection in this case, what we're most worried about, what I'm going to have you solve for, is the x, because that's what we have in our equation. And our x value here, we know that our y's for each line, your f of x is going to equal a certain y, which will equal the same y value for your g of x. In other words, both lines are going to have this y value. We're looking for that point where they come together. If we set your equations equal to one another, so your first y equals this, and your second y equals this, you can use this to solve for x. And we're going to, let's see, if I want to solve this, I'm going to subtract the x. Let's get rid of those lines, because they're not meant to be divided lines. It was just for me to emphasize. But I'm going to subtract x, and if I do it on one side, I do it to the other. And I get rx minus x plus a equals 0. And then let's go ahead and subtract the a over. So I get rx minus x equals negative a. I'm going to come over here where I've got a little bit more room. I'm going to factor x out of my equation so that I have r minus 1 equals negative a. And hopefully you see where we're going with this by now. I'm going to divide by the stuff that's not x. And notice this equation almost looks like this one here. What I can do is I can factor a negative out on top and factor a negative out on bottom. And when I do that, I get negative r plus 1. And my negatives, because I've got one upstairs and one downstairs, they're going to cancel. And I get a over, and I'm going to rearrange this to 1 minus r. Okay, so what we're going to do is we're going to use this equation for the rest of forever. And again, this is your last lesson before your midterm. We're going to take that next class. And I am going to give you the practice test and the midterm at the same time, and just give you so many days to finish both. Alright, so let's say that I want to move into your homework. Now, for your homework, hopefully by now you've figured out how to get to it, but if you haven't, you're going to log into ALEKS, and it's going to take you to a screen like this, and over here on the left-hand side, you're going to see all of your upcoming work. It will have you focus in on the next thing that's due, but I would say just go ahead and knock all these out. They're pretty easy assignments. So for your homework that we're doing with this lesson, that's what I get. We're going to do infinite geometric series, which I will access from my portal because I'm assigning this before, or I'm making this video before it's officially assigned. So I'm going to go to my infinite geometric series, and I'm going to do a preview just so I can get some sample problems from them that will look like your homework. And I see now that I don't have markup, so I am going to use this. Still got stuff from an old lesson on here, but we'll go ahead and clear that off, maybe. There we go. And I'll use this as my workspace. Okay, so it tells you compute each sum below, give exact values, not decimal approximations. If the sum does not exist, click no sum. Now, the most important thing here is your sum will, there's only one time that your sum will not exist, and that is when your series diverges. So, in other words, your line y equals x, and the line that has to do with your equation, ax, let's say I got that backwards. And the line that has to do with your sum, rx plus a, if they're going apart, it diverges, and there is no sum, or rather your sum is infinity. Now remember, that only happens if your r value is greater than 1. And like I brought up before, technically greater than the absolute value of 1. You can have a number that is a let's say that your r is 5 over 4, or rather is negative 5 over 4. If I left it just as r is greater than 1, then it would make it sound like this would work, but the truth is, because this is greater than 1 here, it is a sum that will not work. Alright, so your only time you will diverge is if your sum, if your multiplier is greater than 1. So on this first example, we have 4 times negative 3. I'm writing it out again on purpose so that I can show you some things. Plus dot 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 equals. Now I see here as I move from this term to this term, I'm multiplying by negative 3. And I multiply again by negative 3. And I'm going to keep that up. That means that my rate here is negative 3. Now, does negative 3 meet my rule for divergent or convergent. -3 is going to be something that does not fall into my rule, that r has to be smaller than negative or smaller than 1. To converge. The absolute value of -3 is 3. That means that this function will diverge. If I pull it up on my equation here, then I have a starting value of 4. Almost got it. Starting value of 4, and my rate was -3.